Working with Buro Happold since about 3.5 years. Before that, I was working in Dubai for about more than 20 years with one of the biggest company, the local company, like Safarini. So Anil Hira, he's my boss. Really, I'm impressed with him, and he has been also been involved in all tall buildings of Australia, many tall buildings in Dubai. And also he was involved in 1 kilometer tall building of Nakheel. Well, Anil Hira, my boss, he is also very closely associated with CTBUH, Council of Tall Buildings. He has lots of data of tall buildings. He has been contributing a lot to CTBUH. Let us have a look on this slide, the geographical location of tall buildings, the trend of the tall buildings, how it has from North America shifted to Asia and Middle East. Beginning from 1930s, it was 1930 to 1990, most of the tall 100 buildings were mostly located in North America. You see this blue. And hardly few buildings started in 1990s. This is Asia, and Middle East started in hardly 2000, right? And see, Asia has been catching up with tall buildings in steel since 2000. And you see the trend of structural steel in tall buildings was really tremendous, and it was the only structural steel up to 2000. And from 2000 onwards, the use of structural steel really was going down, and especially and the tall building trend in North America gone down to 20% in 2012, and now taking up from 2000 into 2012, coming up in with Asia and Middle East. So right now about say 42% or 42 buildings out of 100 tall buildings have been built in Asia, and about 32 buildings out of 100 tall buildings are being built in Middle East. The trend of construction material used for tall buildings. And again, the study of 100 tall buildings, the construction material used. All this blue is structural steel, and there is our famous concrete, and green is composite. And you can see the trend of structural steel used for tall buildings in North America especially. It was almost up to 1990. Almost all the top tall 100 buildings of the world, they have been using structural steel. You see, from 2000 onwards, see, you have seen a tendency of structural composite, and then starting of concrete from 2000 especially. Nowadays, see, in 2012, hardly 14% of the buildings, they are now built in total structural steel, and about say 32% as of 2012 statistics that shows about composite tall buildings, and pure concrete buildings about 40% of tall buildings. Well, this is the data collected from CTBUH. Well, trends in tall building construction. Cost per unit area, as how it increases, how it affects based on the height of the building. So the total cost of the building, say for example, the gravity. Well, most of the increase is due to the lateral load resistance system. If you see this gray, the flow system is almost uniform for all the height of the building. The only this yellow, the structure to resist the lateral load, the LLRS, lateral load resistance system, is increasing tremendously as you go up to more than 100 floors. Well, the classic examples of total structural steel building is the very first building, Empire State Building of New York, which was constructed in 1931, used about 57,000 tons of steel, and hardly built in about 14 months, which I don't believe. That's taking about 4.5 floors of steelwork per week. This is the information only. And that was built over about 14 months in 1931. It's total structural steel. It was 85 years ago. And the famous World Trade Center is the classic examples of tubular structure and total structural steel solution. Well, steel now versus the concrete. Well, low labor skill and requirements, as in Asia and Middle East, as we have seen the tendency nowadays for tall buildings. It is the structural steel has been decreasing, but you can see the use of composite structures for tall buildings has been increasing, even in India and China nowadays. Well, advances in concrete technology is the main reason. That is, we are getting nowadays 100 plus concrete very easily. So up till 2000, it was really very difficult to achieve M80, M90. And we were just thinking about, designing buildings for M80 and 90. And now even in India, the tallest building here in Mumbai, at the beginning of the design, we were called about along with the main contractor ACC, we were talking about achieving high-grade concrete. M80 was the design. Then the design was further improved by up to M95, which we are easily, achieving on site. M95. In fact, even we are getting many cubes, like more than 100 MPa. So advances in concrete technology from 30 MPa in the previous days to 120 plus concrete is really helping us a lot in changing our trend from structural steel to composite or pure concrete structures for tall buildings especially. And even you see advances in pumping capabilities. See, we have lots of innovations in concrete admixtures now. I have seen concrete, pumped in Burj Khalifa. The super pasteurizers used with, all Geographical triple to plus and others. They were able to pump the concrete from ground to up to 400 meters. And they have shown their capabilities to pump the concrete up to 600 meters. So high pumpability and high advances and innovations in, pumping capabilities, innovations has changed the trend from structural steel again to composite structures. And again, formwork systems, they have, day by day, nowadays we have seen, looking at the formwork systems, what we are getting nowadays, like table form, My1, and so many other things. So especially jump forms. So this formwork systems is also the main reason for switching off to from structural steel to concrete. And of course, learning more towards concrete. Well, a few examples of structural steel in tall buildings, where we can use structural steel in tall buildings, and structural steel will be the best solution. So let us discuss, I will present this. So gravity solutions. So for gravity system, there might be, say some architectural restraints to have large spans to give the flexibility to architects to use more space, wherein for large spans like more than 10 meters, we would rather suggest to go structural steel like composite decking rather than concrete, because structural steel will, of course, I can show you more slides later, how the structural steel is useful in reducing the sulfate of the tall building, reducing the foundations. So this is, shear stores, I believe. The composite metal decking has been used up to level 50, and above level 50, it was concrete. I don't know the reasons, but reasons might be the acceleration. So, and the concrete flat slab was used above level 51. And it was accelerated construction program, and disadvantage the cost premium for additional structural steel material. I'll skip this gravity system. And tall building experts, of course, we know, okay, for tall buildings to get the lateral load system very efficient, engineers, of course, will go for outrigger systems. Outrigger, especially, we design outriggers using concrete, but we end up with, huge amount of shear stresses, like more than 5, 6, or sometimes 8 or 9, 10, wherein there is no solution except structural steel. And concrete outriggers really have greater, disadvantage if you have like a differential axial shortening. So all those things can be eliminated using structural steel outriggers. Well, structural steel outriggers, are really construction friendly. You can take your core concrete construction directly up without any hassle, without any break in floor construction. And if you have like RCC outriggers, you need to have again a break in slip form for additional couplers, shear keys, a lot of things. But here we need few insert plates and few anchor bolts in concrete, and the jump form can proceed. And well, as I said, concrete is really not the best solution for outriggers. In tall buildings, you can see how outriggers contribute. Usually, if you place outriggers in proper location in the tall building, say H by 3 or 2H by 3, you can achieve really very heavy stiffness, and you can save a lot on concrete cores just by placing a single story or double story outriggers, either concrete or structural steel. But I will say concrete outriggers will have really trouble in catering this differential axial shortening problems. Well, composite columns. For tall buildings, we know the basic maximum stresses for all tall buildings, of course, lies the lower floors, and where the lower floors are very premium for marketing. So we use the minimum sizes of columns to reduce the size of columns. Mostly we go with composite columns, and composite columns before the low grade was available. Now high grade steel with jumbo sections are also available. So we can achieve very slender columns at lower floors. That might be slightly construction delay in that, because the two activities will be involved as inserting the structural steel, encasing and concreting. But really it's worth paying for structural steel sections at lower floors and really gaining lots of fillable areas. The thing is, structural steel inserts is also a better option to take care of any possible tension. For tall buildings, especially if the buildings are very slender, and mostly our buildings are slender because of the ratios. Mostly the tall buildings are nowadays approaching like the ratios of 9 and 10, wherein maximum times we get tension in the cores. So tension in the cores or on the shear walls we resist by using steel inserts. That is the best solution. So using huge amount of rebars is not advisable. And high grade of steel is, as jumbo sections are very readily available here, even 455 grade with jumbo sections of about 300 to 500 kilogram per meter also have been used in one of our towers in Dubai. And now for transfer girders, especially for transferring the columns at upper floors, this has been a really new trend with architects. Okay, every time we will be asked by the architects to go for transfer structures. It is easy, of course, but the thing is we need to plan the constructability of transfer towers from the day one. I think the structural steel is only the good solution for transfer structures, because if we design transfer structures in concrete, you will end up with at least 2 months delay in jump forms, and maximum amount of energy you have to spend for supporting the concrete, scaffolding, shuttering, and other things. If you see structural steel, just few insert plates in the jump form, okay, and maybe large. In addition to insert plates, we might have some members in it. But see, with few, just this insert plates here in the jump form, and you will avoid all the shuttering here, scaffolding here, and heavy to cater about 3 or 4 or 5 meters of concrete. And if you use concrete again, so this concrete will be spanning between this core and this core, and placing concrete between the two restraints, and again is a challenge because such a huge mass of concrete has, of course, for sure, temperature shrinkage cracks, because this concrete is restrained between these two cores. These temperature cracks, of course, will not occur at the same time. Usually, you can find the temperature shrinkage cracks, like, say, after 4 or 5 days of removal of shuttering, which very few people identify, because all the temperature shrinkage cracks are hardly about 0.1 to 0.2 millimeter wide. So to avoid such complications in concrete transfer builders, we strongly recommend to go for structural steel trusses, which are very light and fast in construction, easy for erection, light for foundation. King Abdullah Financial District. There are lots of buildings there in Riyadh. Many buildings designed by BH, Dubai. Wherein a few of the buildings where we have racking columns and heavy structural steel outriggers, where we found that the only solution for outriggers and racking columns was outriggers, structural steel outriggers. You can see it was very simple. Few prefabricated structural steel sections with few studs, all workshop builded, workshop fabricated, just erected on site with few nominal scaffolding. Hardly takes a week. So this has been done, this has been constructed, and the time taken to erect this, all these outriggers was less than a week. So similar thing, if it was done in concrete, it would have taken, I'm telling you, more than 2 months. So here again, outriggers, we have, it's in practical applications where we have used structural steel for outriggers. And roof trusses, this is again the trend where architects, they want to bridge two buildings, bridge two gap between the two buildings, construct a building in the air, few floors, and no floors below. Well, this is a growing trend in the market now. And see, for this also again, if you see the structural steel support and structural steel trusses or mega trusses or verandil trusses is the only best solution to reduce the weight, to reduce the scaffolding, shuttering, and to reduce the construction cycle. Again, KFD, we have few racking columns for few of the buildings. Where we have seen that the structural steel was the only solution to cater this. Mega tall towers in Middle East. It was 1 kilometer tall tower, Nakhil. It was designed by Anil Hira. It was not totally designed. There was peer review contribution by Anil Hira, and unfortunately this was not built. Foundation was casted, barrack piles 1 meter by 2.5 meters and 1.5 meters, all the barrack piles casted, but all the foundations are buried because of this, all this cash flow in Dubai, and all this 1 kilometer tall building, the foundations are buried. But I will go through the design. I will, you don't ask me questions about it because it was all, it's Anil Hira's contribution. I can talk more about, you can ask me more about Princess Tower. It was designed by me from the concept to construction. It was the tallest residential building of the world in 2012. So let me go through the slides. Nakhil, Mega Tower, it was 1 kilometer tower, designed as a tube-in-tube system, RCC, composite columns, few mega columns inside, not shown. It was, you see the diameter of the building was 100 meters, 1 kilometer, the aspect ratio is 10, accelerations no problem, drift was fine, everything was fine. So even Burj Khalifa, if you see the base of Burj Khalifa is so wide, 650 meter tall Burj Khalifa has no any acceleration problems because the base is so wide and the aspect ratio is less than 10. And here also the same, but structural, if you ask me, the structural steel has been used in belt trusses as lateral load resistance system, and few of the gravity girders and also to control the differential axial shortening with slot holes in the junctions. This is to allow the differential shortening of the buildings. Timely, like say every beginning of the year, 1 or 2 years, you need to monitor the axial shortening, and you can again readjust here to cater all the secondary effects due to axial shortening, differential axial shortening. And trusses have been used for transferring few of the columns in plant floors. Again, these are the deep trusses used to plant columns. And this is the Princess Tower. Started in 2006, completed in 2012. In fact, at the beginning, the construction was very fast. And again, in 2009, it was like almost stopped for 2 years. And again, construction started. This was covered in Guinness Book of World Records as the tallest residential building of Happold in 2012. This is a pure tube and tube structure, complete concrete tube and tube, closely spaced columns around the periphery, and very slim core at the center. This core for 107 floors tall building, you can imagine the thickness of the core was hardly 500 millimeters at the basement, and it was reduced to 250 millimeters at the upper floors, above 50 floors. So this is hardly contributing to the lateral loads, and if you see the outer tube is really doing the maximum job. You can say about 90% of the lateral loads are resisted by the outer tube. Well, this we have achieved by working with architects from the day one and giving lesser amount of elevation area to architects for the cladding. Like say it was a constraint to give 40% to an elevation as exposed area. So it was good for structurally using closely spaced columns. In these columns, the clear spacing was about 2 meters. 2 meters is fine for a window, sliding door, fine. And you see for architects, it's 10 meters and 10 meters both sides. It's a very good space. And in fact, during construction, there were about 2 or 3 times revisions in the internal layout, the architectural layout, and nothing affected structures. So this is the really advantage in construction as well as to a great extent to architects. It is so flexible that you can change the internal layout of partition walls any point of time. And the last slab, it was casted in 2010, and I will talk about accelerations later. It was total RCC tube and tube, and the maximum concrete grade what was designed as M90, but we achieved about 90, more than 90. Many places in the basements level and even up to just about the podium level. The podium was about 8 floors. So M80 grade of concrete was specified up to podium, and above that it was M70 and reduced to M50 last. 100 slab is located at 390 meters, and the top is a dome of and the diameter of the dome was about 36 meters. And you see all the top floors, about 5 floors, were total structural steel, the columns, the floating columns, the girders, transfer girders here, from here to the roof, or it's total structural steel solution. And the core, for construction for core and the central core and for the outer tube, two different jump forms were used, and the inner jump form was flying like say 12 to 14 slabs ahead of the concrete grade slab, and the outer tube was flying 8 or 9 slabs ahead of the RCC grade slab. And the construction cycle was really very efficient at the beginning. And if you see the decking what we have used, I have not shown the decking, yeah. The span was about 10 meters from the central core to the outer tube. We have used composite decking there, and the composite decking for 10 meter span was really very efficient design and using this latest free software of Chorus and Fast Track, and using the basic methods of AISC, ASD. We have really designed the beams very efficiently, and for 10 meter span, the depth of the beams was hardly 457. So I need to run few slides. The layout, and see we have used ComFloor CF80 to span 4.2 meters. 4.2 meters, the span of deck. This is, this will reduce the number of insert plates, number of fin plates, number of welding in the core, and the number of props to the beams, even the number of beams. You see the number of beams hardly spanning 9.5 to 10 meters, and few beams are 11 meters. This 11 meter beam is about 520, UB 520. Most of the beams are 457. So let's skip this slide. CF80, let me talk about the decking. At the diaphragm, the decking was about CF80 plus 90 millimeter topping, and the diaphragm was sufficient for 90 millimeter topping to take all the wind loads. As all the beams, the floor beams was, spanning along the wind direction, that also helped. But see, 3 inches topping, 90 millimeter topping was more than enough to transfer the wind loads to the central core. This is the construction, wherein the main contractor was ACC, and the structural steel subcontractor was Eversendai. Eversendai was really, in fact, working on 4 floors simultaneously. The first one is the decking here, and then the second is the primary and secondary beams. The third is the main primary beams. The fourth is they were working in the fin plates, welding of fin plates to the insert plates. So we achieved about 4-day cycle at the beginning of the project, but it was slowed down due to cash flows. But really 4 days per slab was really efficient. And the top dome, about 35 meters dome, and the top, all the penthouses. This is for the Prince of Saudi Arabia. He has taken top 2 floors. All those floors were, it was total structural steel solution. The concrete tube was stopped at 94th floor. From 94, complete the total, the structure was structural steel, and you can see the amount of, the shear keys which we have been used to transfer the shear to the RCC belt and RCC columns. So it is more comparison between the 2 buildings. If you see Elite Tower, which was 90 floors, designed by me, and this Princess Tower, 10 floors, it is designed by Safarini. This Princess has all the floors, composite decking, and this Elite Tower, you can see the floor plate almost same, 36 by 40 meters. This is about 39 by 35 meters, slightly less. But if you see, this was the similar layout. It was tube in tube, and the gravity system was PT slabs, thickened at the edges, slab being about 250, I believe, with thickening in the corners, in the ends. And if you compare these 2 buildings, the foundation of this building was in fact lighter than this. The number of piles is slightly more for Elite Tower. Okay, and for Elite Tower, this being total concrete solution, we have used steel inserts at the lower floors, and we have not used any steel inserts here for 415 tall buildings. So this is a very basic thing there. Okay, usually for tall buildings, we know the dead weight of the concrete buildings usually is around 18 to 20 kilonewtons per meter square, and wherein if you use composite decking, you can bring it down to 14 or 15 kilonewtons per meter square. It's a good saving, about 5 kilonewtons per meter square, because the decking hardly is about 3 kilonewtons per meter square. And if you use solid slabs will be 6.5 to 7 kilonewtons per meter square, plus beams, plus columns. So you're you're saving about 5 kilograms per meter square, okay, of the dead weight. So it's about 20 to 25% of self weight reduced. So reduce columns, reduce foundation, and reduce time of construction. Well, same, the top floor, the building being very slender, we have provided damper, so tuned sloshing water damper. Just I want to show you these, the actual E values. It is not related to structural steel. We have used actual E values tested on, in lab, taking from the site samples, and we have used the same E values we have used in analysis. So the predicted frequency through our ETAPS, it was whatever it may be. So as the measured frequency, which really during commissioning of damper, we found it's hardly varying about 13%. So the frequency of the building for this composite floors, it was really almost matching to the actual frequency of the building. So I will end up, I hope the time is up. We have few more. For all penthouses, it's fine. Can I go for 2 minutes? So a few of the projects here in Mumbai, wherein we have proposed structural steel for top penthouses, and that is the only good solution because we have lots of transfers, almost all the columns for transferring. So steel decking and composite columns was the best solution for the construction point of view, but I'm really not sure about the steel and the cost. So there are a few figures, really I'm not sure about it. So I'll skip and stop because I've given lastly, it was last minute, right?